about layered Chern-Simons theories and fractons.
Okay, so I hope everyone can hear me.
Yep.
And the sharing works. All right, so let me first thank the organizers for putting up this nice workshop. So today I'd like to talk about fractonic and compressible phases in this layered Chern-Simons theory. And most of the talk will be about the compressible phase. And I'll just say briefly about something about the fractonic part. Okay, so and here are a couple of references. So this first paper that we put up last year was mostly about the general setup and all the fractonic part. And we're working on the draft about the compressible state. Okay, so let me go straight to the theory that we want to consider. And hopefully will become clear why this is an interesting theory and to study. So let's think about an infinite, in principle, infinite number of 2+1 gauge fields, but they are in different layers separated in the z direction. So this is a three-dimensional system with many different layers, and each layer hosts 2+1 U1 gauge field. Okay. Now, these different gauge fields are coupled together. So there's some kind of locality in the z direction. So each gauge field is assigned a layer index. And we couple these different layers by mutual self or mutual Chern-Simons terms. Okay. Because of locality, we only couple layers with the neighboring ones. We can have, and in this talk, I'll only be considering self-coupling, coupling between the same layer and coupling between neighboring layers. So the theory looks like this. You have ADA between gauge fields from the same layer and from neighboring layers. And here I is a layer index. Okay. And this should be thought of as a three-dimensional system. And I'll use this K-matrix representation to compactly write this theory. So this can be generally written as a symmetric integer matrix K, and the diagonals are just the couplings between the same layer, and the off-diagonal ones are the coupling between neighboring layers. Okay. And this theory was studied in the context of quantum Hall physics back in the early 90s, and also by later in around 2000. Okay, so wait, doesn't really. Okay, so let me first briefly discuss the spectrum of this theory. Okay, so to really see the spectrum, we need to add some Maxwell terms. Otherwise, you get some fine-tuning results. Once we add Maxwell terms, the spectrum of the photons takes its form. So it's obviously going to be anisotropic because the z direction is very different from the other direction. So x, y are continuous, but z is discrete. Okay. You get this spectrum. And depending on these parameters, m and n, which are just integers, you get either gapped photons or gapless photons. Okay. And the matter sector is generally gapped. Well, with some caveats that we'll come to later. Okay. And with U1 gauge theory, we can always ask about what are the monopole operators, and these are labeled by a magnetic charge vector, okay, L, which just tells you what are the flux of this monopole under each of these gauge fields. Okay, and you get a gauge invariant monopole operator only when this magnetic charge vector, which is an integer vector, when it's a zero mode of this K-matrix. And for this particular choice of the K-matrix with only diagonal and the nearest neighbor of diagonal, you only have a finite set of values for the ratio m over n that can possibly give you, these zero modes. And this is going to be important. Okay, so this is the theory and the spectrum. So why are we interested in this theory? Well, so for one reason is that if we are in the gapped regime, then this represents an interesting, this represents somewhat a fracton phase in the sense that the ground state degeneracy grows with a number of layers because you have all these Chern-Simons coupling, but the way that the ground state degeneracy grows is quite unconventional. When the number of layers is large, it grows as this function. And you see that with the general choice of m and n, this is going to be the base of this exponential is going to be, the base of this power is going to be an irrational number. Okay? And you can also calculate braiding statistics between, for example, particles carrying gauge charges under these different gauge fields. And even though these gauge fields are supposed to be localized, we think of them as different layers, the braiding statistics is not strictly local, actually only kind of exponentially decays with the distance between the layers. I see this exponential here. Okay. And it's also generally irrational in the thermodynamic limit when we take n to infinity. And the physical reason for this to happen is that the actual string operators, if you think of the string operators that create and move these excitations in real space, they are actually not strictly localized in one layer. They actually have a tail that spreads in the z direction. Okay? And this kind of z support of the string operator, the exponentially decaying support of the string operator, gives you this somewhat unconventional braiding statistics. Okay, so this represents, this resembles physics of the fractons in the sense of you have infinite number of supersaturation sectors, and the particles are all moving in a plane, right? Because we start from 2 + 1 Chern-Simons series. Okay. But it's an example of non-foliated fractal models, and also, well, we believe it's beyond, possibly beyond this defect network construction. This is all I'm going to say about the gapped case. So from now on, I'll be talking about the compressible phase, which is somewhat unexpected. And before that, let me first start from, well, switch gears a little bit and give you a microscopic realization of this theory. There are a number of ways to realize this microscopically. You can actually write down quantum Hall wave function, at least in the gap regime, gives you a reasonable quantum Hall wave function when m and n are both positive, okay, and satisfy this gap condition. Or like what we did in this paper last year, we can start from a stack of integer quantum halls and gauge some U1 planar symmetries. You can also construct this Chern-Simons theory this way. But what I'm going to do is to use a slightly different construction that is easier to analyze and to make some of the symmetries manifest. So it's going to be a couple wire construction. So the couple wire model is a quite popular way to construct topological phases in both 2D and 3D. And the construction starts from an array of wires, one-dimensional gapless bosons, essentially. And just because we know 1 + 1 systems very well, we have all these powerful tools, bosonization in 1 + 1. It allows to access some of the strong coupling physics once we allow these wires to interact. So we start from these wires. Each of them is just a gapless boson in 1 + 1. Okay, so C = 1 free boson. And then we couple them in this way. So it's a cosine term. So coupling is somewhat complicated. So the details are probably not that important. And we turn on all these couplings between all these terms that are just shifted over the whole lattice to get a translation invariant model. Okay. All right, and again, I'll call this z direction. So there's a particular z direction that's going to be the direction perpendicular to these layers. So we can also analyze the energy spectrum for this couple wire model. The ground state minimizes all these different cosine terms. So I'm thinking about the regime where this cosine term dominates. So you can either make it relevant or just assuming that the coefficient of this cosine term is large. And there are two kinds of excitations one can consider. One is a small oscillation of these fields around the minimum of this cosine term. Okay, and these are like spin waves or phonons, if you like. And these excitations are gapped when this condition is satisfied. Okay, the same kind of condition that we saw earlier for the Chern-Simons theory to be gapped, the photons to be gapped. So you can tentatively identify this with photons. And there are other excitations that kind of tunnels between different minima of the cosine term, and these are the solitons, on the wires. Okay, and these are more localized, maybe not exponentially localized, depending on whether the system is actually gapless or gapless, but these are more localized, and they can be thought of as charges in the gauge theory. Okay, but what I think the most interesting thing is global symmetry of this model. So if we just have a bunch of wires without any coupling between them, then we know that each wire, each Luttinger liquid or gapless boson has a U1 cross U1 symmetry, right? So one of U1 shifts the bosonic degree of freedom phi, and the other U1 shifts the conjugate field theta. And these two U1s have a mixed tooth anomaly. So they cannot be realized microscopically as on-site symmetries simultaneously. So usually I'll take the convention that U1 phi is a boson number conservation. So the symmetry that shifts the field phi is number conservation of the bosons. So e to the I phi is that accretion operator. And then if we choose this convention, the other symmetry, the U1 of theta, cannot be a microscopic on-site symmetry. And what we usually know is that you can actually embed the lattice translation of this 1+1 boson into the U1 theta. So for example, the translation along the y direction becomes just a shift of the theta field by 2 pi times the fading factor of this wire. And this fading factor is the same for each wire and the 3D system. Okay. Now, if you look at this coupling term, the coupling between the wires, when we tune these parameters, these are integers, such that m equals -2n, then both of these symmetries are preserved by this coupling. Okay. And what this means is that, we actually preserve both the U1 symmetry and this lattice translation symmetry along the x direction, and obviously preserves the y and z translation. So it preserves all the symmetries of the system at a particular fitting, at an arbitrary fitting, essentially, because nothing needs to be imposed on this mu for this to be a symmetry. So what this means is that for this particular choice of parameter, this is actually a compressible state. Okay. Now, let me say a couple words about compressible states. So there are not that many compressible states, right? Either it's a symmetry breaking that we know of, it's either, although it's quite ubiquitous, eddy metal is a compressible state, but it's either a symmetry breaking or it's essentially a Fermi liquid. Or you can couple the Fermi liquid to gapless bosons to get non-Fermi liquid, but still it's morally a Fermi, morally you still have the Fermi surface. Okay. And this was recently really kind of made into a very strong constraints by Dominic, Ryan, and Sento, as a constraint on the emergent symmetry of any low-energy theory that can describe a compressible state. That is, you cannot have a compact zero form symmetry or finite higher form symmetry if you want to have arbitrary fitting. And this is just the constraint on the globals, on the emergent symmetry. So for these two examples, in the symmetry breaking phase, like a superfluid, you have U1 global symmetry, zero form, and you have a U1 higher form symmetry. So that evades the theorem because you have a continuous higher form symmetry. Or like in the Fermi liquid, you can have essentially conservation of fermions on each point on the Fermi surface. Of course, this is not a rigorous way to talk about this, but that's the idea. And that also is a huge symmetry that's beyond what's forbidden by the theorem, obviously. So one would ask, one would wonder, what is emergent symmetry and how the anomaly, this fitting anomaly is realized in this case? Well, so before I get to the field theory again, let me first point out that this particular system with this choice of parameter that allows arbitrary fitting, it doesn't have any local autoparameter. Okay. Any local vertex operators that create charge excitations, they always get. So any such operator with local support, they always create gapped excitations. But if you allow non-local operators, you can create an operator that kind of penetrates the whole system. Okay, it's just a boson creation operator that goes through the whole system, multiply them all the way through a system. And this one actually is an autoparameter. But because of this non-local nature, it has a superfluid density that vanishes as 1 over Lz of the number of the extension in the z direction. And just to give some more intuition, if we think about this coupling term and turn off all these thetas, then what you see is just phi minus phi, which is a boson hopping or Josephson coupling between neighboring wires along the perpendicular to z direction. So if we turn off these thetas, then we just get the layers of superfluids. But now we turn on these, we have these thetas, so the coupling is such that there's no local superfluid order in any of the layers, but we will get one that kind of goes through the whole system. So we call it a stretched superfluid order. Okay,
Hi,
so
Meng, sorry to interrupt you.
yeah,
A couple of minutes. Yeah, so you're out of time.
Minutes do I have?
A minute or two.
Okay, all right, I'll be done very soon. Okay, so let me now go back to field theory. So we can use a kind of couple wire version of boson vortex duality to show that this couple wire construction actually can be mapped back to this kind of layered Chern-Simons theory. Assuming a finite LZ, then you get this kind of theory as we kind of expected. And depending on the boundary condition, what you put on the top and bottom surface, the K matrix around these corners may look slightly different, depending on whether you break the symmetries or not. Okay. Oops, this is a problem. Sorry. Yeah, I'm already. All right, so this is going to be the last couple of slides. So let me very quickly run through the symmetry analysis of the Chern-Simons theory. So given the general Chern-Simons theory, we know that there are many symmetries. For example, you have zero form symmetries, the global symmetries, by just mixing these different gauge fields together by a GL transformation, and that may become, for example, permutations of anyons. There's also the U1 topological symmetry, the conservation of fluxes. Here I just choose a particular charge vector. And there's one form symmetries of shifting these gauge fields by a flat connection. And here, in particular, if the K matrix admits a zero mode, there's one form symmetry. There's a U1 one form symmetry. Okay, that parameterized by this zero mode vector. And there's a two-fold anomaly between these two U1s given by this 4+1 action. Sorry, given by this 4+1 action. The B is a two-form background and A is a one-form background. And V and T here are the charge vectors and also the zero mode vector. So we can show that when we take this particular Chern-Simons theory, assuming that there's only finite number of layers, and we can show that while you can correctly describe the Philling anomaly using basically this U1 cross U1 symmetry. Okay, so once you choose a particular background for the two-form symmetry that corresponds to that once you for particular two-form background, once we turn on some kind of gauge fields for the translation symmetry and also has this mu in it, and then the total anomaly basically encodes the Philling factor of the system. And this coefficient here grows with the number of layers. So that's how we see that the 3D systems actually have the right Philling factor. So essentially this U1 cross U1 is from this stretched superfluid that I discussed earlier. Okay, and we can also analyze the other boundary conditions and get results consistent with what we expect from this Philling. So I want to mention that there are many other examples. Actually, once we think about this couple wire construction, it's not that difficult to get compressible states. Okay, and these are this physics is we haven't really understood these systems quite well yet, but these are probably interesting to consider. Okay, so this is a summary, and sorry for taking too much time. Okay, and that's all. Thanks for your attention.
Thank you, Meng. Thank you to both speakers. So